Hello again. Thank you for joining us. Welcome to the world of predictions. Natalia and Wojciech, floor is yours.
Thank you. Hello everyone. Today, together with Wojtek, we would like to present the topic of reconciliation that we recently explored in our forecasting project. Reconciliation is a branch of hierarchical forecasting that focuses on providing coherency between the different levels of hierarchy. First, we will give you some insights into forecasting within our Nestlé team. We will explain the reconciliation challenge we ran into, compare our initial solution with new reconciliation methods, including mean trace, Dirichlet regression, and empirical weight adjustment approaches. And finally, we will discuss the results. First, to give you some context, let's briefly introduce our team. Data Science Hub is the Nestlé Poland team that delivers machine learning solutions across the whole Europe. Data scientists, MLOps engineers, and product owners work on various projects such as demand forecasting, manufacturing optimization, and other data-driven business challenges. Before we dive into reconciliation topic, let us give some highlights about the reason we decided to discover reconciliation methods. The aim of operational forecasting project is to create a time series forecasts for the demand of the product groups for each retailer. Product groups are segments of similar products. We do the forecast in weekly buckets so that demand planners can send a correct production plan to the factories for the nearest weeks. We deliver our solution to 11 European countries for 8 categories, like pet food brand Purina, confectionery, and beverages. Although all our forecasts have been deployed for several years, we find new opportunities for improvements. One of them is the disaggregation from product groups to products after our forecasts are created. On the plot, you can see the historical demand for a sample product group. The stacked bars represent the demand for each individual product within that group. We generate the forecast on the product group level because of the availability of exogenous data like promo, but our demand planners need more granulated forecasts on the product level as well. Previously, we split the forecast by the historical proportions on the product group, but we realized that we lose the forecast accuracy on this split because the DPA, the weighted mean absolute percentage error, was lower by 20 percentage points compared to the top level. This observation brought us to the exploration of the reconciliation methods. Going more into details, our initial solution that was implemented several years ago was based on historical proportions. We calculated the average sales proportion for the last 26 weeks for each individual product in the product group. The forecast for each individual product was the multiplication of its historical proportion and the top-level forecast. The main issue with this approach is that it assumes the sales proportion within a product group is static, while in reality, these proportions change over time due to seasonality, promotions, and shifting consumer trends. So let's go through the plan of our experiments. First, we will show you mean trace and Dirichlet regression, and at the end, we will show you our approach, which is empirical weight adjustment.
And to evaluate those experiments from our database, we have sampled a group of over 1,000 product groups across multiple markets, and each group contains between 2 and 37 products. That's giving as a result several thousand of them. And also we can see that most of weights in this historical data is close to 0, so which makes allocation and splitting more challenging. And to split this data, we created train and test set. Train set contains 42 weeks, and test set is 10 weeks, with forecast generated 3 weeks ahead at product group level. And our task is to split this forecast to individual products. So that's the aim.
Yes, and our first experiment was minimum trace. Mean trace is a top-down reconciliation approach that generates coherent forecasts across a hierarchy by minimizing the trace of the covariance matrix of reconciliation errors. Its objective is to minimize the sum of variances of the reconciliation errors across all levels of the hierarchy. Mean trace operates on matrices. The summing matrix, which defines the hierarchical structure and maps bottom-level forecasts to all hierarchical levels. And base forecasts vector, which contains all initial independent forecasts from all levels. This method calculates the reconciliation matrix that minimizes the trace of the forecast error covariance matrix. The reconciliation process works as follows. Projection to bottom level. The reconciliation matrix projects base forecasts from all hierarchical levels down to the bottom level, minimizing the trace of error covariance matrix. It creates reconciled bottom-level forecasts that optimally combine information from all levels. And then the reconciled bottom-level forecasts are aggregated upward. And please notice that the heat maps you see at the bottom are not the covariance matrices. These are correlation ones. We showed it in order to show the effect of the mean trace method. The first heat map displays the correlations between forecast errors across our product hierarchy. Essentially, how forecast mistakes at different levels move together. You can see their high correlation values, many in the range 0.7 to 0.9 range. It means that our forecast errors aren't random, they are systematic. When we overforecast one product, we tend to overforecast second product as well. This is actually valuable information because these patterns mean our forecasts are predictable and mean trace can exploit that. After applying mean trace reconciliation, look at what happens to these correlations on the right matrix. They drop significantly. Some dropped to the level of 0.3. So mean trace used those original error patterns as a roadmap. It identified which forecast levels were most reliable and adjusted the reconciliation weights accordingly. Lower residual correlations mean mean trace successfully removed the systematic bias from our forecasts while maintaining coherence across the hierarchy. This translates directly to the better forecast accuracy and more reliable planning. Moving on, let's explore another technique, Dirichlet regression. Dirichlet regression directly models the proportions as draws from Dirichlet distribution, which is based on the geometric space where all proportions sum to 1. So you can imagine probability vectors that sum up to 1. The key insight is that we parameterize the Dirichlet concentration parameters as functions of covariates. So instead of modeling each proportion independently, we are modeling the shape of the entire distribution. Dirichlet regression brings some advantages. It uses Dirichlet distribution to model proportion uncertainty because proportions aren't fixed. They change over time due to seasonality, promotions, and market dynamics. Dirichlet regression captures the correlation structure between proportions. If one product takes a larger share, other must compensate. Secondly, it maintains non-negativity and sum to 1 constraint. You can't get invalid proportions. The Dirichlet naturally respects the unit sum constraint. And also it generates probabilistic forecasts with uncertainty quantification. Unlike point estimates, Dirichlet regression produces complete probability distributions over proportion vectors. You get the entire distribution, not just a mean prediction. Moreover, you can have different covariates influencing different products' proportions. Maybe product A is more seasonal, product B responds to promotions differently. The regression framework handles this naturally.
And to help you better understand the approach we are proposing, let's take a look how weighted mean absolute percentage error at the product level relates to forecast error at a higher hierarchy. And this equation describes WMAPE on product level, but it's reaggregated to product group level. So to take into consideration all products contained in this product group, where WI is forecast weight and SI is weight of actual sale. Then we can also write equation for triangle inequality, and we can write it in this form. And when we combine those two equations after field transformations, and also knowing that this sums must have sum to 1, we can show that the achievable weighted mean absolute percentage error is bounded by relative error on product group level. So difference between forecast and sale is the error, and divided by sale is a relative error. So that's the knowledge we get, that the best result we can get is related and not less than error on higher hierarchy. And to make this concrete with a simple example, and so let's consider a product group with two products, P1 and P2. The relative error at group level is 20%, meaning that forecast overestimates sales by 20%. So once we want to plot this relationship, on the plot, how assigned weight for a given product affects this reaggregated WMAPE, we know that this cannot be lower than this bound. Additionally, we know that a true weight of P1 across time series is 0.4, and we will use this knowledge as a reference point. And once we plot the relationship between assigned weight, we can see that there's a range of weights that we can assign to a given product that guarantees the minimal achievable error, and this range is because of the error on the higher hierarchy. So this minimum value of weight is offset by error we got on product group level, and maximum weight takes into consideration the additional forecast that we can add to this product, still guaranteeing that the error we get is minimal. And how can we use this knowledge to create our method? So at first, we can go to the next slide to plot the compute distribution of weights for a given product based on historical data we get, and associated with it cumulative probability. So this takes into account the possible skewness in the distribution. And when we get the forecast on higher hierarchy and some initial forecast weight for this product, we can define using values described earlier, the minimum and maximum weights. And when we can show them on the plot, we can compute or calculate associated cumulative probability of those edge weights. Then, when we take the mean value of these two probabilities, we can get the associated weight. So when we convert it using the inverse CDF function, we can get the weight adjusted. So effectively, weight adjusted is its median value in the range between these two edge weights. So this approach takes into consideration takes into consideration skewness of the weights that we can get from historical data, and also takes into consideration error associated with forecast on higher hierarchy. And to summarize this framework, we can sum it in these 4 points. So at first, we know that this framework is agnostic to initial forecast weight source. So we have to begin with estimating this weight using some method to do it. Then for this chosen method, we compute a relative error over time for product group, so for hierarchy, and then we also build empirical distribution of weights for each product to take into consideration the possible skewness. Then, knowing this relation between error and possible weighted mean absolute percentage error, we calculate edge weights. Then, using a cumulative distribution function, we select the final adjusted weight, and then we can use this adjusted weight to allocate forecast from higher hierarchy to lower, in our case from product group to product level. And the methods, initial methods for this framework that we have used is moving average. So that's the method that we are using so far. And the other approach is Dirichlet regression as a source. So the inputs from outputs from Dirichlet regression. And also we propose ensemble method, which is just an which final weight is average of outputs of those two methods. And when we want to now we can compare all the results that we achieved using different approaches, and we will compare them against our current approach, which is moving average or moving weight. And the lower we get, the better, basically. And for weighted MAPE on product level, we can see that adjustment methods gives us the most, or rather gives us improvement in terms of weighted MAPE. And for bias, basically most of the methods gives us the improvement comparing to moving weights approach. And also we can see an additional benefit of using methods that generate forecasts a forecast that's is not taking into consideration constraints of summation to 1, and we can aggregate those forecasts back to a higher hierarchy and compare them with original forecast we get. And as we can see, when we do it for weight adjustment methods, we get also improvements in terms of product group level error. And to combine metrics that we use so far, we use scores called here combined error, which is just the sum of weighted mean absolute percentage error and absolute value of bias, to get the final comparison of all these methods. And as we can see, weight adjustment methods and ensemble, which is combination of these two, finally ensemble gives us the most improvement comparing to other methods. And also this behavior can be seen on higher hierarchy, as we can see when we take into consideration also bias, the higher hierarchy error also gives us the improvement. And as a result, we can see that ensemble method achieves the lowest error. So in conclusion, we have decided to implement this in our production environment.
Yes, so in conclusion, our initial solution that was implemented several years ago, moving average, was not sufficient. So we explored several reconciliation methods. And it turned out that our methodology, empirical weight adjustment, can improve the combined error by 8 percentage points. Yes, and we are going to deploy this method of empirical weight adjustment in our project in our countries that we deliver our solution. And the key takeaway is that empirical weight adjustment method leads to about 1% inventory reduction. So it turned out that we managed to improve the inventory. Yes, and that's it from us. So thank you for watching, and if you have any additional questions, you can reach out to us tomorrow at the stand. Yeah, so thank you.
Thank you.
Thank you very much.
Thank you.
We have still, I believe, a few minutes.
Yeah.
Maybe now, and we have some questions in the chat. What forecasting methods were used? Only MA? What about all components or ARIMA or other methods?
Okay, so first, if it comes to the product group, models that are used are light GBM and ADIDA for intermittent time series. So these are models that were used to generate the forecast on the product group level, so this higher level. And for the split, there were these methods that we showed on the presentation. So initial solution was moving average on weights. We also used it in min trace for lower hierarchy. For higher hierarchy, these were the models explained at the beginning, so light GBM and ADIDA. Yes, so min trace helped us to remove the error in the covariance matrix. The second model was Dirichlet Regression, yes, which models the probabilities of each individual product. And in this empirical weight adjustment, it is our method that is based on the historical weights and also includes the relative error in order to find the best weight for the individual product forecasts.
And also because of the distribution of weights, and most of them were close to zero, ARIMA-based models were because of high correlation, and we also use some inverse centered log transformation for those weights to have this constraint in ARIMA models, but it caused that it's even for simple orders of ARIMA, it was computationally ineffective. We got a lot of errors, and ARIMA-based approach, we decided to not go further with them.
Yes.
Thank you. Maybe we still have time for another questions. Do we have any? I cannot see any other questions, so thank you very much.
Okay, so thank you very much also for having us here, for the invitation. Yeah, and yes, if you came up with any other questions, you can reach out to us tomorrow at Stance or at LinkedIn. Yeah, so thank you.
Thank you. It was a pleasure to have you. You get a lot of thumbs up only on the chat.